My name is Janu Verma. I'm talking about transfer learning in NLP. Really thanks Sanket, Lakshan, other people for organizing this. This is like third iteration, and I have been privileged to be a part of this right from the first time PyData conference was organized here. So as I said, I'm going to be talking about transfer learning in NLP. So just a disclaimer that these are not like my slides in a sense. I mean, of course, I created them, but I have borrowed a lot from other people, and I was in a rush like to create these, and last minute rush, so I forgot to essentially add all the attribution and all. So just a disclaimer, I will mention people that I have borrowed from, and I will add attribution to the people, and release the slides in the final form. Okay. So before we go into transfer learning, right, this is like first 3 slides I borrowed from my talk last year. So what is machine learning, right? I assume a lot of people here are interested in machine learning, right? So machine learning is a field of like, computer science, you can say, or statistics, mathematics, which what it does is that it builds systems that can automate a task, right? So that can like, given some amount of data, that, a system that can learn from it, okay, that can automatically extract some patterns from it, some information from it, okay. And the tools that we use here are like, statistical and mathematical in nature, right? So as people are all aware. And primarily, I'm going to be talking about supervised machine learning. In supervised machine learning, you have some label data, okay, that is used. So you have some data points and you have some label for them, okay. So example is like, maybe we want to design a system to classify images of animals into cats and dogs, okay. So cat or dog is the label for it, okay. And in supervised machine learning, we would build a system that will try to learn from a set of labeled images, and it will extract the pattern so that it can make decisions when it sees an unseen, it sees a new image, okay, whether this is cat or dog. Okay. So a typical machine learning pipeline, and I will come back to this also, is basically starts from the top, right? So you have some training data, okay, and training data has, just take the previous example, it has images and it has whether it is a cat or a dog, right? And then we have a machine learning algorithm. It could be any algorithm. Okay, it could be convolutional neural networks, for example. So we are using this training data to train the algorithm. By training, I mean that one by one a data point is fed to the algorithm. It sees an image, and then image on the way the algorithm is designed. It will have, maybe it starts with a random initialization, so it will have some weights, and on the basis of that, it will predict whether this is a cat or a dog, right? So if it predicts correctly, then there is no penalty, but if it predicts incorrectly, then there is a penalty, right? So that is what we are doing here, that whether it is it learning that or not, right? And based on the misclassification or based on the error, right, that is fed back to the model, okay. So then like we learn that, right? So we do this loop, right? So we fed it one image, another image, and it sees, right, and slowly the weights are updated. Or in other words, the parameters of that algorithm, it could be any other algorithm, the parameters of that algorithms are updated till they reach some optima, okay. And it's an optima which is given by this data, right? It's directed by the data that we have at hand, right? It could be a global minima or maxima, but very rarely it is, right? Okay. So typical machine learning pipeline, okay. Another example is of machine learning, supervised machine learning, image classification. So maybe not just cats and dogs, maybe bunch of other categories that we want to classify images into, right? Classifying documents, articles, news articles, whether this is about sports or entertainment or legal or politics. Right? Other examples that we see on in our daily lives, Google search, Siri, okay, email, like spam detection, okay, Google Translate. Okay. So lots of other, right, like the social media that we use, right? So we are, essentially what I'm trying to say here is like we are surrounded by, machine learning. Okay. See machine learning all over in our cell phones that we carry in our pockets. But there is a problem with supervised machine learning, right? Like, so we have, come this far and we have developed these tools, but still today, like, big machine learning, big research labs or big players in machine learning are like big corporations, right? Like the work Google is doing, okay? Google, Microsoft, Facebook, right? So it's still not very like, democratized, if I may use that word, right? So there is a limit to, to the extent that we can push supervised machine learning, right? So the biggest problem is that it is heavily dependent upon data, right? So you would need some data. You do need label data, okay? And the current, like with the current paradigm of deep neural networks, right? So these are very, very complex models. So they do require a lot more data to be able to train well, okay? So machine learning, supervised machine learning is very domain and task specific, right? You train a model for image classification, okay? So, and you train a model for image classification, and if you want to, can you use that same model for image classification? Like if you have trained a model for image classification on ImageNet, for example, right? So which is supposedly well representative of the real world, right? But can we use this in like a slightly different domain, like maybe image classification in agriculture? Okay, can we identify like agriculture crops or maybe diseases in the images of crops, right? Or animals, for example, right? So can we do that, right? It's very, very task specific. It's very, very domain specific. So by domain, I mean, for example, medical images, right? So medical is the domain, and then the task is the image classification. But maybe you want to do another task, right? You have trained a model for image classification on, say, ImageNet, but now you have, it's the same domain, same set of images, but you have a different task, right? Maybe you want to localize objects in the images, right? Okay, maybe you want to find like where, not just that there is a cat in the image, like where is the cat in the image, okay? Maybe if you have multiple images in that, right? Can you use that? You would need like more data for it, right? You would need label data. You would need data which will have, an image and the bounding box of the cat, right? You would need like an image and like all the objects, right? It could be multiple objects in that. So you would need that sort of label data, which we don't have, okay? So I chose a different example, but over here I was thinking about self-driving car, right? Like say you are designing a self-driving car, and first thing you notice that maybe you are designing the system in some city where there are a lot of cars and a lot of and there are pedestrians, right? So you want to identify whether there is a car in the view or there is a pedestrian in the view, right? Or is it just the background? It is good to go, like the car can drive, right? And such, these sort of systems could work, right? Like, but if you say, like, I was just thinking about that, like in New Delhi, right? Like, a lot of people commute on two-wheelers, right? So, can you use that same system, right? Now you have added an extra label there. You do need some label data for that, okay? So, it's very, very, again, like reiterating that point that it is very, very domain specific and very task specific, okay? We have made some progress in this direction, and that I will talk about, but that is the major problem, right? Like we cannot iterate fast, okay? I don't know like if there is any talk here which is on unsupervised learning or anything, right? Like, so it's just like that is the direction we want to go, right? But still a lot of the problems that we are solving fall under supervised machine learning, but we don't, we have this problem, okay? We cannot move domain, we cannot even move the task, okay? There has been some progress in this direction, which is the crux of this talk. So what is something called transfer learning, right? It's just a stupid name for saying that can you transfer, your learnings from your knowledge from one task or one domain to another, okay? So for example, like if same example, right? Can we transfer the knowledge that we have learned for building a three-way classifier, image classifier, which can classify whether this is a car, this is a pedestrian, or this is the background? Can we use the same model to include also two-wheelers in it, okay? Can we do that? Can we create a model so that we don't have to like redo all the work, okay? That is the best we can hope for, okay, at this point, okay? So that is what the transfer learning is, right? Like it seems very, very fancy, but at the end of it, if we have trained one model for a task, can we use this same model, okay, or some knowledge from this model, right? Whatever this model has done, the machine learning model, what it's doing is like extracting some patterns. So can we use some of those patterns, some of that information in a related task, okay? So far we are not, and I will restrict myself to here, like, two related tasks. So like, going from cars and pedestrian to cars, pedestrian, two-wheelers, okay? Maybe that sort of example, okay? Of course, there is a lot of work in like going across domains, right? Like ImageNet, using a convolutional neural network trained on ImageNet to medical data, okay? There has been some work, we are still, but I will not talk about that, okay? So somehow what we do is that, as I was saying, right, like machine learning algorithm, like when we are training it on some data, right, it's learning some patterns, okay? So idea is to encode this knowledge, encode these patterns, in some, like in some features, okay? And that features can be used in another task also, in another domain also, okay? And like philosophically, I'm making an assumption that there is a notion of like some universal features, okay? There is, features are very dependent again upon the task, data, domain, everything, right? But if there are some universal features, okay, and can we learn those features, right? When we are training a machine learning algorithm for a specific task, can we sort of extract those features? And even if these features are not universal, can we like, not start from the scratch and use these features as the starting point, and so that maybe we can fine tune these features to obtain the best features for the task B, right? Okay. So I have obtained best features for task A, okay, best image features for image classification. And now I want to do object detection. I want to detect images, like I detect objects in the images where they are, okay? And I can still start with these features. These features are not universal, so I cannot just take these features and do this at task B. But I can always take these features and start from there. Okay, the algorithm is iteratively learning some features, so it will not start from the scratch. It will not start from the zero. It will start from this set of features which were universal, which were sort of best features in a different task. Okay, so mathematically, like you have local minimas, like so. You are starting with your values of parameters which are at the local minima of a related task. Okay, so you're not starting from random initialization. Okay, so it's not a local minima for this, but the thing is that what has been observed empirically is that you are at a position where you wouldn't have to do a lot of work to go to the local minima for new task. Okay, so in some cases you can go really fast. Okay, so you can go very quickly there, and by quickly I mean maybe time wise, or maybe you don't need a lot of data for that. Okay, so to be able to train ImageNet, you do need a lot of data, but maybe for this whole thing, right, for the other problem, if you start from an initialization from model trained on ImageNet, maybe you don't need a lot of data. Okay, so this also, like what it does is that it's sort of like, you can also do, right, like image, and I'm talking a lot about ImageNet because a lot of work has been done in that. Okay, so anyone here can download a pre-trained ImageNet model. Okay, it's available. It comes with all standard, neural network libraries, right? So anyone can download, and you can have like a very different domain. Maybe you are interested in agriculture, you are interested in medical, you are interested in like a very obsolete domain that no one is paying attention to. You can look at that, right? And you can, start with the model which was trained on ImageNet, which was pre-trained on ImageNet, and you can fine tune it to your specific task without having, to need a lot of data, right? So you don't have a lot of data, you can still, hope to do that. Okay, and there has been a lot of success stories for it. Okay, so okay, like traditional machine learning, right? Like you have two tasks, okay, task or domain, right? A and B. What you will do is that you will train two separate models. One model for cars and pedestrians, another model for cars, pedestrian, and two-wheelers, right? There was no bridge, right? And as I said, right, like can we encode the knowledge that we have gained after training one model, after doing this lot of work, can we use that, right? Can we use that in another domain, right? Like human beings think that way, right? Like so, if we see a two-wheeler and then see a bike, and we see some similarities, right? See like a motorcycle and a cycle, we see that these both of them have two wheels and all, right? So we don't need we don't really like need separate models, right? And something we always believed, but we were never like really able to do that. Only after some success stories, some examples were demonstrated empirically. Okay, so can we find a bridge, right, between two different domains, two different tasks? And I'm saying different, but they are not very different. Like they're still related. At least that is where the modern research is. Okay, so like again, it's model trained on ImageNet can be used for self-driving car, some biological data, right? So there's a lot of work on like doing radiography using machine learning, okay, using computer vision, okay, looking at your blood samples, the pictures of blood samples, can we do something over there? So there has been some work in that, okay. There are some success stories also. but I will not say that, we have achieved that, okay? So we have not been able to completely transfer this knowledge, okay, across like a very different domain, but surely in related domains. Okay. Andrewing in 2016, NeurIPS conference said, in his keynote that transfer learning will be the next driver of machine learning success, right? And a lot of work has happened in past like 3 years after that, okay? So like, he presented this chart, and I would encourage you guys to go watch this video. It's on YouTube, right? So his idea is like, he focuses a lot on like commercial success, right? We're doing a lot of research, right? I mean, I will talk about some of the systems design in NLP and all, but can we really use that in production? Can we really do something with that, right? Like there is really good research. You get a lot of data, like Google has access to a tremendous amount of data, and they have a lot of compute resources also. So they can, for example, like the transformer and other models I will talk about, but they were trained for like a month or something, right? Not everyone can afford that, right? So can we like convert this, the success that we have seen in academic machine learning, or like in conferences, in research, can we replicate that? Can we make any benefit of that in commercial success? And so this will be transfer learning will be and has been shown to be a major driver, right? It has really helped in bridging that gap, right? Bringing our learnings from research to commercial. Okay. Then we can do transfer learning now in some domains, because we have like, if you think about like, computer vision, right? So we are now doing better than humans, like machines are doing better than humans in a test, right? At least on ImageNet data. So, so we are like, we've come really far, right? So we are, the error rate is less than 5%. And just, just to remind you that in ImageNet, there were 1,000 classes, okay? I don't even remember 1,000 classes, just like, seeing a picture and, tagging it with a class, like it's almost impossible for me, okay? Or speech detection, has also come a long way, right? Like we use these services, Alexa, Siri on our phones, right? Google has a similar service, right? So a lot of work has happened, right? And now it's a good time to ask this question, right? Like, okay, we have acquired a lot of data. These big companies at least have a lot of data. They have trained these models, and what they have shown is that they can put these into production also. Okay, so these systems are working in production. Now it's a good next question as a follow-up question is that, can we, yes, okay, can we put this, in the hands of like, other players also, right? Can we do this, right? Can we transfer this? Okay, can we go from one task to another? Can we get away with this idea of like requiring so much of data to train machine learning models? Okay, so this is like almost a parallel track that is running, and a lot of like interesting work has come out. But this is, at one end you will see top researchers at Google and other companies in academia pushing the boundaries and like, creating these really super sophisticated models, which will, achieve state of the art, right? Like results on standard tasks. But on the other hand, there is this work that can be like, can we create a system with like comparable without losing much accuracy? Can we create a system without requiring much data? Can we, there is another track where people are working on, can we create, a similar model without losing much? Can we create a model which doesn't require that level of computational resources? Can we run it on device? Okay, things like that, right? So it's an interesting time for that, okay? Okay, so I will start with like computer vision, right? ImageNet, are people familiar with ImageNet data, right? So it's a, and this is the headline from, I think it was like Washington Post or something. I should have that. So data that transformed AI research and possibly the world, right? And it is not an exaggeration, right? So after ImageNet was released, it was the first time a data which was representative of the real world that was released, right? Because it was created, it was introduced in 29 by a group of researchers at Princeton at that time. Okay, so the problem is that the data set that we have earlier, did not really capture the variability of the real world, right? If you have like 100 images, 200 images, and you are able to classify them, you can build a model. Can we use that in production? Can you do anything with it, right? It's just very, very, it's very specific. It hasn't really, like the real world is very diverse, right? The images, the things that we want to do, right? So what they did was, this was built on top of WordNet, and I will not really go into details on that. But WordNet is basically like, it's a hierarchy of words. Okay? It's sort of a dictionary. And what they did for ImageNet is that for every word in WordNet, they got 1,000 images, okay, downloaded from Google or something. Okay, so it is very, very representative. It also has a hierarchy that, like, there is a dog, and then dog is an animal, and, like, so it was, it was very interesting. Okay, because at that time the research was like, people would always say that, if you cannot do even one object, like identifying cat or dog was very difficult at that time when this data was released. Okay, and you cannot expect people to to develop models that will be able to identify thousands of objects in the images. So if data is the new oil, as they say, like, it was still dinosaur bones in 2009, right? It was nothing. Okay, so big time, right? This paper wasn't even like published as a full paper, like it was a poster, and then now I think it's one of the most cited papers in CVPR. So okay, so what people realized is, again, like, this idea that I've been iterating, that if you do well on ImageNet, if you can solve, if you perform really well, if you bring down the accuracy, bring down the error on the ImageNet data, then you are very close to solving computer vision. Okay, like at least object identification, okay, recognition, because this data was very variable. This was very, like, it captured the variability of the real world. It was very representative of the data, of the images that we see around. It had like 1,000 categories, and which is ever expanding. Okay, I think the last time I checked, like, for example, Google has a service which was built on top of ImageNet. They have 6,000 categories. So there is a lot of categories. Okay, so what people realize is that a lot of, if you remember, like, the models for computer vision or model for image recognition are like stacks of convolutional neural networks, right? So what people observed is that rather than starting from the scratch, like starting with a random initialization and then feeding data points one by one or in a batch or something, right? If you train it, right? If you take a model which was trained on ImageNet data, and by trained I mean it has some values of the parameters, right? Which is, it has obtained an optima, right? If you start from there, and now maybe you have a different task, okay? Maybe you want to do object detection or something, okay? At least the features that you have, at least the parameter values that you have learned in the convolutional blocks, okay, you keep that same, right? If people are familiar with, like, the convolutional neural networks for object recognition, like what it does is that it's basically has bunch of convolutional layers, and then at the end it will like flatten it out, right? It will have like one feature layer, and that is basically a classification layer in the end, right? So all of the features, like, what the convolutional blocks are doing, they're learning some high level features, right, of that image. They're learning some patterns in that image, okay? And then you basically take them out and then define a single vector with that, okay? And that vector is input to your classification model. So what people try doing is that you start with this convolution block. You don't you have it. You start with this initialization. You start with the parameters values that you have obtained after you have, like, by parameters I mean the weights in that, right? So the weights that you have learned after training on ImageNet data, right, on million images. Now you have another task, right? Say you want to now classify cats and dogs, okay? Earlier, your accuracy for cats and dogs, like, if you had to start from scratch, like, you have like maybe 100 images of cats and 100 images of dogs, okay? Then you were not able to train, right? These models are very, very complicated, right? There are a lot of, like millions of parameters that they have, right? So, but now you start with a model which was trained on ImageNet for classification across 1,000 categories. And you take that model, and that is what we call like pre-trained model, right? It's a pre-trained model, and now you feed it like 100 examples, 100 examples of cats and dogs one by one, okay? And you don't start from scratch. You keep updating the weights of these these layers, and at the end you get these features, and you instead of like 1,000 layers, 1,000 layer output, you have like 2 layer output, like 2 units. You have cats or dogs, right? So your task has changed, right? So you want to detect where the object is, right? You can do the same thing, okay? You can have like few examples of label data, which will have like, also have bounded box and all, right? What is it? Left, right corners, right? Of that, cat in that image. So that you don't need, like, you don't need to train it from the scratch. You don't need like a lot of data to do it, right? You can just take few examples, and you already have, features which were really, like, which were like sort of best to for the image recognition task on a large set of data, right? So it is already trained on a large set of data. Now you can improve upon it by adding some more data, okay, for a specific task. Okay. So it has been shown to work really well. Object detection, segmentation, pose detection, video recognition. In fact, across domains also. Even today, like the best model that we are using to to study X-rays or to study blood samples, or across domains like in agriculture and all, are all based on the convolutional neural networks that were developed by ImageNet, right? So again, yeah, I just said this, right? So multiple convolutional blocks, and you can sometimes, like, there have been tasks where you don't even, like, some examples, you don't even train them. Like, it's just like you don't fine tune them. You have already trained them on ImageNet. You just train the last layer. That has also seen some success. So it's just like, you like immediately went from, like, for example, VGG network has like 13 million features, from 13 million parameters to like maybe 1 or 2 million parameters, right? Immediately, you just like froze it. You don't like train. You just trust that ImageNet is already doing great. I don't even need to train it. I will just train this one layer. Okay. And sometimes you want to train like in all of the layers. You can also take like part of the features which were, like the model which was already trained, and then add another part to it, new part, and just train the new part and create like new architecture, which is like maybe very different from the architecture that you started with. Okay. So you can do all these things, right? So it's basically allowing you, giving you time, right? Like, so you can save upon data, you can save upon compute sources, you can save upon compute time. Okay. So you can, leaves a big part of the model, and you say like, I don't have to train it, or at least I don't have to train it from the scratch. Okay. So this is what I really wanted to talk about, transfer learning in NLP. Okay. So version 1 of this, right? Like, yes. Okay. I've some question. Okay. So so transfer learning in NLP, right? So we can do this in images. That's, it has seen a lot of success. There is continual new work that is going on in that direction, but we haven't really seen anything in NLP, right? That is, and the reason I say NLP and I'm interested in NLP, is, or like I'm interested in NLP, or the reason people are interested in NLP for transfer learning in NLP is because other than computer vision, NLP is the other branch that has seen like this other type of data that has been completely revolutionized by deep neural networks. Okay. So can we do that? Can we do transfer learning? Okay. And a sort of precursor to transfer learning in NLP was the work on word embeddings, right? Word embedding is basically we create like a vector representation for every word in the corpus of data that we have. Okay. I talked about this last time also. So it's basically, so we want to create a representation, okay, such that like the semantic similarity, right? If if we want to compare two words, right, apple and banana, right? Can we compare these two words, right? Like we know they are fruit. I at least know that apple is closer to banana than it is to a chair. Okay. So we understand that, right? But like computers don't, right? Like, so it depends on the encoding that we use, right? If you take like these as strings, there is no comparison, like you cannot really, right? So that is one way to look at it, like maybe treating these as strings. There have been other ways to encode textual data or encode words in that, and I wouldn't go into those details like TF-IDF or like count vectorization, one-hot encoding, right? So the problem with that is that you cannot really compare two words. Either two words are exactly same or they're not. There is no notion of similarity. But we know that apple is closer to banana than a chair. Okay. But if we use like one-hot encoding, then the similarity between apple and banana is 0. Apple and chair is also 0, right? So can we create a representation of words such that the semantic similarities between the words, they get mapped to, so they get mapped to mathematical similarity in that space. Okay. So example, like if you take like apple and banana, and we take the vector of apple and the vector of banana, and we compute the cosine similarity, for example, between them in that vector space, right? So from the semantic space to a real vector space, and in the real vector space, we can ask these questions: what is the distance between two things? Okay. And what I'm like, the work I'm referring to is called Word2Vec, started at Google. Okay. It uses like these two types of architecture. I'm running out of time, so please look at these. Okay. So surprisingly, what they noted is that they found that it was also like not only like semantic, it was also capturing syntactical relationships, right? So you could like see that the vector of king minus vector of man plus vector of woman results in a vector that is very close to the vector of queen, right? So it's very it was very surprising and very interesting, right? So if people want to talk more about these, see me after this. Okay. So word embedding gave a way to create like, a representation which was aware of the semantic relationships. Okay. And then now we have this. What can we do, right? Okay. So we could do all the like NLP, standard NLP tasks, right? Like text classification, machine translation, okay, search and discovery, Google search and everything, right? Recommendation. A lot of the problems were using these embeddings, these representations, okay, rather than any other, rather than the old like one hot encoding, right? So it was like transfer learning in some sense, but it's a very strong assumption that that the word embeddings have like that these are universal features. Okay, this is a universal representation of this word, right? That is of course not true, right? Because the Apple versus Apple, right? Like it will be a company Apple or an Apple, right? But it will have same representation because every word will have only one embedding there. Okay. But it was, in a sense, transfer learning, and it has really revolutionized the field. So I'm not trying to say that, yeah, so it was a remarkable idea, right? Really helped. Even if you use, like I have myself at my work, use just straight off, like just, use the word embeddings for the word that I could find in my corpus and use for text classification. They performed really well. They performed better than the other ideas, okay? So it has been very, very valuable. Like Google search was like, essentially running on it. Lot of like text classification, NLP tasks. Okay. So language modeling, entity recognition, all kind of, NLP tasks. Okay. But the problem is that, it's just like we are only looking at, again, like this is an Apple versus Apple situation, right? Like where is the context? Okay. There is no context. Okay. Can we just like, can a single, embedding suffice, right? Like we do need more embeddings, right? We do need to know the context of the conversation because it's very hard to think of like universal features in textual data, right? Because you and I have very different writing style, speaking style, so it's very, very dependent, okay, on the context. But somehow the context was used, but it was just used in the first step, and then it was completely ignored, and then we have only one embedding, right? So this is, I'll just take like 5 more minutes, and so this is something I really want to talk about. So, so if you take like word embeddings as like step 1, okay, it somehow helped us. Okay, it's helped us in a lot of tasks, but it had like very strong assumptions. Okay, and it was not very practical. Okay. I was able to transfer this. Okay, you can also like create systems like semi-supervised systems where you start with word embeddings as the initialization. Okay, Google word embeddings, and then you iterate. Like maybe I had a project where I was working on medical data, medical text. Okay, and we started with the Google word embeddings, and then we fine-tuned them, as we were training for our model. Okay, so that can be done. So it has been very, very successful. But again, still, it's not completely transferring, right? It's still very, very, it's completely forgetting the context. It's assuming that we have universal features, which is like a very, very strong assumption. So and the big problem, why the transfer learning in NLP has been very slow, or why like people did not really pay much attention to it earlier, is because like you always have this like you have a is because like there is a lot of variability, right? As I was saying, the different typing styles, different writing styles, speaking styles. So what I'm trying to say is that the distributions are very different, right? So it could like so it can happen like in many situations that you have in one domain or one task that that the data you are working with is different, and then it has very different distribution than the data you are trying to move it to. Okay, then the domain that you're trying to move it to. Like I work with I work a lot with like chat data, like how human beings chat, like send messages and all, right? So that is very like people are very colloquial. Some people skip spellings, right? So vowels altogether. So it's like very, very different data, right? So can we like, so that has always been a problem, for transferring one domain to another. Okay. So I want to say like a lot of work has been happening here. Okay. So very, very, very quickly, I'll just take 3 more minutes. Okay. So, okay. So you could use like, word embeddings have been used in like sequence to sequence models, for example, right? So by sequence to sequence model, I mean like a machine translation maybe, right? Question answering system, right? So what this model does is that it's basically has like two blocks, right? One is an encoder, so it takes an maybe a French sentence, and encodes every word in it. Okay, creates an encoding representation, and then this encoding representation, this is one vector which is fed to the decoder part where it is generating new words. Okay, in maybe English, like which is the language we want to translate to, right? Okay. So in many cases we use like LSTM or RNN based encoders and decoders. Okay. Okay. So a sequence to sequence like a translation model would look something like this, right? We'll take like words one by one, create like in hidden state. People are familiar with the RNNs or something, right? And then the whole encoding input will be fed to the decoder, and then it will create like, every word will be created iteratively by looking at this encoder and then the hidden state, right? So this the encoding vector acts as the input to the as the hidden layer. Okay. Okay. So I'm told I'm running out of time. Okay. Okay. Just 1 minute then. Last thing. Okay. Cool. So we can, so transfer learning in NLP, right? We can create these sequence to sequence models, right? You can also create a sequence to sequence model, as in like if this is the first one sentence, take like a text data, okay? Text article or something. The first sentence, what is the next sentence, right? Can we create such a model, right? Can we create, so you can create a large language model, okay, wherein you have like an input sequence and have bunch of like, LSTM layers, and you are trying to predict the next word. Okay, so you have like 4 words, and what is the 5th word? 4th word, what is the 5th word? Okay, so what people have done is they create a large like language model trained on maybe all of Wikipedia. Okay, so now through this model, what we have done is that we have, when we are training this, we have learned some weights, right? And the second step, you take this same model, and now in a different domain, the new data that you have, you fine tune it. So you again feed the new examples, the new data that you have one by one through this. Okay, so it is not starting from zero, it's not starting from the random initializations, it has already been trained. So this will be made public, you can download it, the first part. The second part does not take much time because we have much smaller data. And then in the third part, maybe you want to classify documents, right? So in the second part, you just fed like 3rd to 4th word for your data also. And in the last part, it is a classification problem that you're trying to solve, okay? So it's always the same idea, language model, and there has been a lot of work in this, different iterations. And sorry, do talk to me if you have more questions. Okay. Thank you.